Welcome to Geospatial Data Ingestion at Scale with Geobeam. I'm Travis Webb, Solutions Architect at Google.
And I'm Matt Forrest. I am part of our solutions engineering team here at CARTO.
Great, thanks, Matt. So this is what we're going to be going over today. To set the stage for what we're doing here, I'll spend a few minutes and give you an overview of some of the geospatial cloud components that we will be working with today. I'll talk about what they do and how they work together. The title of this talk, Geospatial Data Ingestion at Scale, represents a problem. It's not easy to do. I'll talk about some of the reasons for why this is and some of the challenges our customers are asking for help with. Then I'll introduce Geobeam, a tool we built to offer one potential solution to this problem, and show you a demo of Geobeam in action. And last but not least, I'll hand it back over to Matt to talk about some of the real world use cases that he's been working with customers on. So let's dive in. Geospatial Cloud is Google Cloud's suite of geospatial capabilities. This suite includes the data to power advanced geospatial analytics and machine learning, and the tools to help you deliver novel geospatial insights. So let's look at some of these tools and data sources and discuss what they can do for you. If you look at the left hand, yes, it always starts with data. You can integrate with all the places you are getting data currently, along with the 50 petabytes or so of the data that Google brings to the table in the form of analysis-ready data sets available in BigQuery and Earth Engine out of the box. BigQuery is our cloud enterprise data warehouse, and Earth Engine is our platform for earth science and data analysis. To operationalize geospatial insights, we have Data Studio and Looker for BI and reporting, Apogee to help you build custom applications based on your geospatial insight. And we also love how CARTO builds on and extends BigQuery to deliver custom applications and insights. And they also bring to the table a full data observatory, which contains a large number of data sources that you can add into your geospatial applications as well. Of course, in order to get the data from the data sources on the left-hand side over to the data warehouse and reporting tools on the right side, you need a way to do all the geospatially things you need to do, like transforming and vectorizing and validating your geodata in a managed way at scale. Although geospatial ETL is complex, we find that GIS professionals often have a pretty good workflow figured out for them for getting data from point A to point B, but it often takes a lot of effort to get there. And incorporating new data sources and destinations into that workflow takes even more effort. There's a lot of custom scripting and automation, and there's a lot of management and maintenance overhead for many of these traditional GIS pipelines. It's true that modern machines have big drives and lots of megahertz and can handle fairly substantial local data sets without much of a problem these days, usually. When I talk about scale, though, I'm talking about being able to combine your proprietary geospatial data with the petabytes of data that's publicly available in cloud services like Earth Engine and BigQuery, and from proprietary data sources that come from inside your company and from partner data sources such as the CARTO Data Observatory. I'm talking about being able to train machine learning models using geospatial time series data. These things require considerably more resources than are available on any single machine anywhere. Being able to closely integrate your GIS workflows and applications with the huge amount of data out there presents an enormous opportunity to develop new analytics, new insights, and build new applications that deliver differentiated value to the business. But with power comes responsibility. It presents new challenges operating at this kind of scale. as a result of both tooling and hardware limitations. The solution here is not to try to bring all those petabytes of data into your existing geospatial databases. Solution is to bring your geospatial data into the cloud. The result is that you can ingest and process geospatial at scale with Geobeam and build pipelines to load spatial data into BigQuery or anything else that Dataflow connects to, because Geobeam adds GIS capabilities to your Dataflow pipelines by enabling you to run GDAL within Apache Beam. Now, one of the really cool things that we've learned at Google over the past 20 years is that the solution to a problem at scale often allows us to apply that same solution to benefit smaller workloads as well. So Dataflow and Geobeam don't just work at scale, but at any scale, from megabytes to petabytes and everything in between. So having a unified way of handling your data makes management and automation and maintenance a whole lot easier. So let's see it in action. I'd like to share with you a quick 5-minute demo of what using Geobeam is like in practice.
We're going to start by kicking off a Dataflow job. I'm using a pre-built container that contains Geobeam and all of its dependencies, which includes GDAL and some other libraries. I'm specifying the location of the input file, which I've already loaded into a cloud storage bucket. This is a GeoTIFF raster file. It is from the digital elevation model dataset provided by the U.S. Geological Survey. And I'm going to load this in through Dataflow, and Geobeam is going to take this raster image, polygonize it, and store each pixel or group of pixels as a polygon in BigQuery. Here we are in Dataflow. Our job is getting started. One thing I really like about Dataflow is that you can easily monitor the status of your job, read logs, and generally see how things are going. Our pipeline here consists of 4 steps: read, elev to centimeters. This converts the elevation, which comes in as meters, into centimeters. Format records, which creates rows that can be inserted into BigQuery. And then at the end, the write to BigQuery step. Okay, so our job has finished. It's successful. Now let's go over to CARTO, open up the CARTO workspace, and load in the data from BigQuery that we just stored through Geobeam. First, I have a parcel table that I loaded in from a shapefile, also through Geobeam. And I'm going to get this loaded in just to visualize and identify a particular parcel that I want to get more information on with respect to the elevation. All right, I found my parcel, and I'm going to copy this GPIN number because we're going to use it again in just a minute. Now I'm going to create a custom query, and I'm going to join these two tables together now. The new digital elevation model table that I just loaded in and my existing parcel table. I'm going to join it on an intersection with the parcel geometry and the elevation geometry. This is going to give us only the elevation measurements within this parcel boundary. And I like this editor because it, it gives you notifications when you've done some syntax error. So we ran our query. We quickly got a result. This is the parcel that I'm interested in. And okay, great. So I've got all my my elevation measurements here, but it's not so easy to visualize and tell what's going on just at a glance. So I can go over to the left and change the style of the layer to render each pixel a different color based on the elevation value. And this is going to give us a really good way to visualize what the elevation of this parcel is and how different regions change in elevation based on the color of the pixel. Okay, so this looks great, and we can easily tell what's going on here. Over toward the right, or I should say east, the elevation values are quite a bit lower. Whereas then if I move my mouse over to the western side of the parcel, the elevation values are much bigger. Now, also I can make this query as complex as I want to. I added a buffer in the intersection so that I get a little bit of additional contextual area around the parcel so that I can understand the shape of the land that surrounds the parcel as well. And I can change the opacity to visualize how this elevation data interacts with other features on the map, such as the shape of the building.
All right, that was a quick overview of Geobeam. Now I'm going to hand it back over to Matt to talk about some of the real world use cases.
So we have been using Geobeam at CARTO to work across lots of different use cases, and traditionally working with really large or complex data, both raster and vector, has been a challenge. Traditionally, working with raster data requires a long thought out process. And it's not something you can quickly grab a sample file from and start working with it in a matter of minutes. Geobeam has changed that for us. It's also enabled us to work directly and intermingle vector and raster data sets very easily. Some of the key use cases we've started to see where we can use this data together are listed here. So that's analyzing climate resiliency in our communities and for infrastructure projects. And we'll show a quick demo of what that looks like, but that's another case where combining that raster and vector data, specifically raster data that's been analyzed to provide some deeper insight. Second is ingesting and updating floodplain data. If you're familiar with FEMA floodplains, they're very large scale data that go to a granular level. Being able to quickly grab and use that data and intersect it with lots of other data sets has been a challenge because of the scale of the data and the complexity of it. Ingesting telco coverage data. This is something we've seen where telecommunications providers have really complex, raster data sets that are in, very odd or diverse formats. This is something that GDAL is really built for, to manage lots and lots of different types of geospatial file types, and it works perfectly for this, especially at the scale that we're talking about, where we have very small scale rasters that might be just a handful of meters. We can easily take that data and start to analyze and visualize it. And then the last is actually connecting to Esri server. With Google Cloud, we can actually develop and orchestrate these workflows to sync to and read file types, no matter how large or small, that are connected to other GIS systems. So if you're already using a geospatial server within Esri, we can easily start to use that within BigQuery and connect to that and automate the entire process. So what that looks like, here's a sample of a workflow that I actually was working on. I'm going to the MN Topo or Minnesota Topo website and actually grabbing a quick sample of a raster file here. So I can draw my polygon and quickly grab some data. I'm going to grab a 3-meter DEM, download it, and send it over to my email. We've actually orchestrated a complete workflow. I can actually take that GeoTIFF file, upload it to Google Cloud Storage, and then kick off the entire Geobeam process behind the scenes with that and Cloud Functions. And we've seen here is that I'm actually taking that into BigQuery and building a tile set using the CARTO spatial extension. And now I'm actually viewing that DEM file, and I can actually click in here and start to see, okay, what that looks like, and create a tile set that I can build into an application or visualize. And all this data is also available behind the scenes as well. So it's basically from raw GeoTIFF to tiled map within about 30 minutes. Another use case here is actually starting to look at different resiliency projects. So what you're seeing here is a view of the island of Hawaii, and we're actually taking this road sample. I believe this road is Highway 83 in Hawaii, and what we're actually intersecting that with is both raster data sets, things like elevation above the certain area, And then other vector data sets that are also complex in scale, looking at erosion modeling or sea level rise modeling. And then other risks, looking at lava flows and volcanoes. And what you see here is actually we, in BigQuery, created a control point every 200 meters along the road. We can actually see for each point what's the relative risk that we can associate with that. So it's sort of a risk index. And the darker orange areas have lesser risk. The brighter yellow areas have higher risks. You can actually see that varies greatly along and across the island. And as we start to zoom in, we can see some of our different data layers here. And going deeper, we can actually see some of these specific points. Where inland, we have less risk. As we move along the coast, we have greater risk. And the final one I love is Global Forest Watch. This takes in complex raster data sets that are built by and modeled to show different things like tree cover gain, loss, land use, climatology. You can actually focus in and pick out specific areas or counties and actually do a really nice spatial intersection there. We can visualize this over time. All of this is, like I said, combining these two different pieces of data, the vector boundary state data sets and then raster data sets that combine this complex imagery data and allow us to visualize it in the map. When we go deeper, we can actually visualize this over time. We can create reports, and then we can actually compare that and look at that with satellite imagery. I think what's great about this is that this raster data was previously not so accessible to the public. Now we can create it in a format where many people can view and interact with and study it, something that really wasn't possible before. And that's what we love about being able to use all this data, solving these complex problems and taking it together. And Geobeam is sort of underpinning all of that for us. So we hope you enjoyed the talk. Geobeam, you can check it out. It is available on GitHub. And then if you have any questions, you can always reach out to Travis and I.
Hi, Matt. Hi, Travis. Thank you so much for that overview of working with large amounts of raster data and then having some really cool visualizations on the front end there. So I know we're a little over time, but we do want to get a couple of questions in as the chat. We have a few. So we'll start with how critical are the open source tools within Geobeam, and how does Apache Beam help those scale to the massive data that Dataflow can handle?
Yeah, I can take that one. The open source tools are very important. They're the foundational elements of Geobeam and Dataflow. So Apache Beam is an open source toolkit that Dataflow, which is a service in Google Cloud, is built on. There's two big pieces. There's a bunch of smaller ones underneath, but GDAL, the Geospatial Data Abstraction Library, does a lot of the GIS sort of wizardry underneath. And Apache Beam leverages GDAL to split up your geospatial input files into a zillion little pieces, and it uses Beam to farm out the computation on each of those pieces onto hundreds or thousands of different machines. So you can process really large input files in lots of chunks, and then it merges it all back together at the end to produce your result.
Wow. Okay. Fascinating to learn about how all these different tools kind of work together to make this possible. So thanks for that. Maria in the chat asked, hi, the accuracy of the analysis, is it being reported on the fly, or does the user access the accuracy of the results?
Both. So you can certainly log things in Dataflow if you run into, if like you're assessing data quality as it comes in, and then you can see and evaluate the results as they come out. Matt, anything you want to add on that?
Yeah, and sort of the last piece is when you're looking at the analysis, that can be managed and analyzed in SQL once the data is actually in BigQuery, so you can use SQL to kind of look at your data in more detail too. So.
Awesome. And then I know we've been talking about working with big data, but what's the largest data set that you've ingested?
Matt, what have you done so far?
The largest one would probably be like a 30-meter granularity raster data set. I think it was upwards of the final pixels, and some of those pixels were merged, keep in mind, was like close to 150 million actual individual components, and certainly it could go much larger than that. But I think that was the when we're talking one single file, that's the largest I've worked with.
Okay. Yeah, as an example, we have a customer in the agriculture field that they've loaded in one sort of single run, they've loaded several terabytes in. That's not huge data, but being able to load a few terabytes in an hour or so is a pretty significant improvement over existing tools. And those few terabytes of data input results in about 25 billion rows of data in BigQuery. So that's individual pixels or groups of pixels.
Absolutely. So it sounds like people are getting to work with big data sets that otherwise maybe this wouldn't have been possible by using the Dataflow and Geobeam workflow. I think we have time for one more technical question. Do you have to define the data schema, or can it be read from the data?
I think also both. You can define it in advance. Geobeam also includes a bunch of tools that leverage GDAL to auto-detect the schema of the input file. If it's a raster file, it's somewhat simpler because you just have a number of bands. If it's a vector file, then GDAL can inspect that file in advance, generate a schema, and then you can use that to build the schema for your BigQuery table. And Matt was a contributor for making some of those tools a lot easier to use. So thanks, Matt. It's power of open source. Anyone can contribute and make it better.
Definitely.
Cool. So thank you again, Travis and Matt. That was a wonderful presentation.